community of people from different fields, all interested in similar problems. As you said, yeah, we talked today about another side of my research. Usually I give talks on other sides, but I'm doing some new marketing today. And the title is Strategic Interaction Across Scales from Autonomy to Future Mobility. So the standpoint from which I start is that we are developing autonomous systems. In particular, we are in a conference for robotics, so we are developing robots with the goal in mind for them to have positive societal impacts, right? And here we see some of the many examples or the many success stories of this technology. You have autonomy for autonomous vehicles, you have space exploration, you also have very small robots that are used to monitor environments or even catastrophes and so on. Now, what I look at in my research is this fact that the societal impact of these new technologies actually depends not only from the way we develop the technologies, but also from the design together with the existing systems and the interactions with the existing systems. And a particular example of this is when you imagine developing a technology for mobility and embedding it into a very complicated system, such as a transportation system. And here in this context, we always have the heaven and hell, right? For autonomous vehicles, for instance, we have all the promises. We say we will need less cars, public transport will be enhanced, thanks to this technology, and also these vehicles will be safe and more affordable. On the other hand, instead, we see that when implementing new ways of mobility to perform mobility, you might incur in congestion, or the actual computation required for this kind of vehicles will make them very unsustainable, right? So we always have the two sides of the coin, and we have to find a balance between them. And what I do in my research is I look at tools to co-design these systems, because my philosophy is that single components are slowly well understood, but it's very hard to understand the complex interactions between those. And another thought is that if you think about it, and I think it's also clear from today's talks, we are getting closer to natural sciences as engineers, right? Because we are developing some technologies and then we are studying them after we have created them, right? And this is interesting, but also poses some challenges. So today I'm going to focus on two important challenges for decision making at two different scales. The first one will revolve around behavior specification for robots, following the principle that if we try to develop the same rules for robots that we have for humans, we have to be a bit careful. And the other is going to be about interactions in larger systems. So I will first talk about behavior specification, and we'll then touch base very quickly on mobility systems. The reason why I put them still in the talk is also to have this catchy title from autonomy to mobility, but it's going to be more about autonomy. And I'm going to solve an optimization problem in this talk, which is you won't see many formulas. Actually, I think maybe I have one. I will make the talk understandable. We'll try to convince you to use the tools I'm presenting, and also so that people that have jet lag like me can get through it without too many headaches. And all I'm talking about today you find on my webpage. All right, let's get started. So the problem I want to talk about is behavior specifications for autonomous vehicles. And the reason why we need tools for that is that around this topic, there is a lot to be considered. If you think about requirements, you have things ranging from the specific function of the vehicle to ethics, safety, liability, compliance to traffic rules, which are different in every country, courtesy, comfort, culture. And it's very hard to take these things into account in a formal framework. If you look at safety alone, how this is usually approached from the point of view of safety or of regulators, it's that you certify vehicles and drivers, you put in place some rules of the road, and then essentially you have enforcement. You have authorities and a legal system that give fines and punish you if you violate the rules. However, those rules are also open to interpretation and depend on certain contexts, right? For instance, if you take one of the axioms of the rules in Switzerland, it says that all the road users must behave in such a way not to pose an obstacle or danger to other road users, which is fine, but that also means that sometimes you can violate certain rules such that bad things cannot happen, right? So who decides which are these rules? What are the metrics? What is safety? The general things that do not work well for autonomous vehicles in particular are three. One is art constraints, right? Because you don't want to be in a situation in which the vehicle receives a message saying unfeasible. Anything you can do is unfeasible because the vehicle still has to do something, right? You don't want to have art constraints. And also, apart from certain cases, it is very hard to find guarantees when you have infeasibility. The other bad thing to do is case analysis, right? I think we have learned in past years that there are so many things that might happen in your system that case analysis is not the way to go. And another thing that it's tempting, I know, but relaxing your objectives, put everything into a single cost function can work in certain cases, but if you want a decision system which is reliable in any scenario, this might be prone to overfitting. And also, if bad things happen, it's going to be bad for transparency. You don't exactly know why something happened. And so you might say, okay, but what should we do? Are we screwed? Like, can we do something about it? So one approach sometimes is to solve a very complex problem and then to throw the ball at other stakeholders. Say, okay, I'm giving you this tool, and then you are a regulator, you decide, right? I'm not sure we should do that. The other thing is that's dangerous is trying to incorporate our own beliefs in the algorithms we develop. Instead, what I'm going to present today goes towards creating a transparent system, which is customizable depending on the situation, the country, or whatever you care about, and goes towards an opening versus stakeholders, so towards engagement. And the history here starts some years ago, where the concept of minimum violation planning was introduced. Actually, one of the speakers today, Yana Tumova, was one of the first people working on this. And here the idea was to starting from the fact that you could violate some rules, or you could have some infeasibility, right? And you don't care just about infeasibility, but you care about the fact that sometimes you might violate some constraints, and you want to look for the decisions that violates them the least. So in particular, technically, what was done was defining a rule, or defining a total order over certain rules. And then the idea was to order the behaviors based on these rules. For instance, if you think about a taxi driver cares about safety, compliance, comfort, and finally performance, whereas a race car cares more about compliance, slightly less about performance, safety, and then comfort is not really that important, right? And this was a practical tool because it allowed people to define behaviors in a modular way. It was easy to predict what a car would have done in certain scenarios, so you could validate the behaviors. And also, it was easy to understand when the car was not behaving well, why that was the case. But we have many situations if you think about the road scenarios, in which some rules are not comparable or are indifferent to each other. And so what came later as some line of work was an idea to take pre-orders or partial orders to allow the incomparability between two rules. So now, instead of having just the possibility of putting one above the other, you also have a way to make them uncomparable or making them indifferent to each other. So let's take the example that you might encounter in Switzerland. Oftentimes, you are driving, there is a cow in the middle of the street, and you want to order your trajectories based on some preference. Here, the partial order that's given is a partial order that says that collision is the most important thing you care about. Then there is area violation and clearance, but those two are not comparable. So in this context, B and C are two trajectories which are totally symmetric, right? So they are indifferent to each other. You clearly prefer all trajectories over the one that actually collides because you care about collisions. And actually, B and C are not comparable with D, right? In one case, you have very little clearance from the obstacle, and you do not violate the area. In the other case, instead, you violate the area, but you have large distance from the obstacle. And this is like a toy example, but it has been used in practice. How to use this in practice mixes two things, creativity and good taste. And this follows this slogan, which says that the way to get good ideas is to get many ideas and then to throw away the bad ones, right? So very, very practically, if you think about a motion planner, it has a part which is a trajectory proposer, something that creates ideas and with creativity. And then you have some way to assess how good those trajectories are, and these are the scores, and it is where the partial orders play a role. And so in practice, what was done was, so those things are patent. There is a way to take the rules of the road for most countries. You can aggregate them into 100 rules, and you have almost 20 rule groups, and you can create partial orders. And each company or each society can decide which order is the most important one. Now, this was cool, but somehow takes only into account one player, right? It's a motion planner for one vehicle. What I want to show you quickly now is a situation in which you have multiple such players. So obviously, we are all working on different kind of games, and that there are many nuances that distinguish them. But essentially, the setup is always that we have some players that have a scalar cost function. Then based on certain preferences or certain dynamics, people select an action. Given the joint actions of the players, we can understand what's an outcome of this game, and then we have some equilibria that we can investigate. What we developed was what we call posital games, where instead of having a scalar function, now players have a partial order function. So instead of having just a scalar, they have partial orders of preferences over an arbitrary number of metrics they care about. And the particular setup in which we investigated that was what we call trajectory driving games. So here you have different vehicles, they have different priorities, and they have to essentially choose which trajectory to pursue. And this cartoon shows that different vehicles for different usages might have different preferences. Now, as I said, these slides hides a lot of mathematics, a lot of technicalities, but I want to give you the main message, and then I'm happy to discuss offline. Essentially, we were able to extend standard notions of game theory to the case in which you have partial orders. The first cool thing was we were able to design sufficient conditions for equilibria to exist. In particular, you can show that these games are potential games under certain reasonable assumptions. It is cool because now with these preferences, we have a way to characterize the efficiency of the admissible equilibria. And the final point is the most exciting for what has to come next, which is now we have a formal way to perform behavior specification and also preference refinement. So the idea is that if you can start with an idea of what the preferences might be, like I can go on the road assuming nobody's a suicidal driver or these kind of things. And then based on my observations, I can refine these partial orders. And there is a result that says that the refinement of the partial order also refines the equilibria of my game, right? And this is something we have many case studies that show this, but essentially refining those preferences means that we have a certain number of operations we can perform on these partial orders, and these operations preserve the equilibrium and actually shrink them. And the one side of the extreme side of a spectrum is that you scalarize everything into a single cost function, right? But that would only happen at the end, not at the beginning of the process. All right, and towards the end of the talk, I will talk about challenges ahead because that's what we have to work on. But now I want to switch gears to the second sneak peek of what I wanted to show you today, which is that right now I was talking at the platform level. I was presenting something at the platform level, but in my research, I'm actually interested at looking at different scales, right? You can think, if you keep with the same metaphor, I could think about a vehicle, but then I could think about a service with many vehicles, and then I could think about a city in which I have many different services interacting, right? And here the challenge is that actually we don't have the same kind of agents, right? Here in this cartoon for Boston, you see that you have really different players that not only reason differently about the problem, but also they have different cost functions, which are really different, right? For instance, you have mobility providers, liability companies, policymakers, academia, us, right, industry, and everyone not only models it in a different way, but really cares about totally different things. And it's just not just about a small parameter in a cost function, right? And so what helps when looking at this problem is that if you look at it from the public sector point of view, it's clear, right? As a city, you want to meet sustainability goals, define the public investments. If you're a politician, you want to be re-elected, right? You want to guarantee quality of life, these very big points. And typically what you can do is regulate, put policies in place, decide pricing for public transit or incentives and taxes. Instead, as a private sector, you want to design your technology to capture the customers. You want to make money, right? You want return on investment. And typically here, you can design the technology, you can decide the pricing, or you, for instance, you can decide exactly how the service will look like, fleet sizes, fleet compositions. And so the interesting bit here is that the interactions between all those players vary a lot if you change the time horizon, right? On a daily basis, some might have more actions than others, but on a yearly basis, things might change, right? Maybe the municipality has more actions in the yearly frame. And how we deal with this problem is via sequential games, right? Here, it's very intuitive, actually. You have a municipality that plays first in this game describing society and sets the rules of the game, for instance, regulations or incentives for certain services to be developed. Then you have the mobility providers that react by themselves taking action, deciding which service they want to design or the prices they want to offer and so on. And in the end, there is the mobility system. And now what happens is that the payoff for the lower level model really depends on what you use as a model. And that's like, if you worked a bit in transportation, you know that this last piece never reaches consensus, right? There is people solving optimization problems to model what the travelers would do. There's people working on micro simulators. There's everything, right? And the idea when we developed this was really to be agnostic of that. We only need a way to evaluate, given certain policies, what happens when those policies are put in place. So those are Stackelberg games, and you can compute the equilibria via backward induction. So I want to show you a very, very simple example. Let's take the city of Berlin with the realistic network. We take realistic demand and congestion effects, and we also take realistic numbers for all the parameters involved. And now we assume we have these mobility providers. So we have a municipality, an autonomous mobility on demand operator, micro mobility operators, and a normal taxi company. Now, if you can compute the equilibria between the citizens, so the ones traveling, and these mobility on demand services, you see that very rapidly the number of equilibria explodes. Right here, for instance, you have equilibria with respect to the revenue for the private companies, the cost for customers, and the actual emissions. So somehow we have all the three entities involved. And the interesting bit is that the last player in the backward induction is the city, right? And depending on what the city chooses as a policy, you might obtain different profiles, right? A customers-oriented city might choose to place itself down there, and this choice goes back to certain strategies for each of the players involved. Or you might have a revenue-oriented city or something else, right? But this framework is a way to reason about the problem. Now, what are the challenges ahead? Well, I think there is a fil rouge between the two things I proposed, which is those are new ways to look at a very complicated problem, but also we are solving the problem in a naive way right now, right? We didn't really focus on the algorithms, we just focused on the modeling. So going ahead, especially for the partial order games, we essentially need to redevelop the tools to solve these games in an efficient way. And importantly, as I mentioned, these games allow you to model uncertainty in a way that was not possible before. So this being said, I want to thank my collaborators at ETH and NCCR for the sponsors, and also take the occasion to do a bit of advertising. So if you're looking for a position, I'm creating my group right now, so I would be happy to discuss opportunities. Thank you. Okay, so let me try to, I can answer how they relate, But is your goal to get the equilibrium of the original game? My goal is not to go back to the original game, right? I'm saying that the original game for certain applications is not enough, right? We don't want that. But I can answer. So the technical contribution here is that although you're taking a complicated way to specify this behavior, you can still construct a potential. It's not nice looking, right? It's a partial order potential, so it's a huge cost function. But this preserves these partial orders. So this guarantees an existence of an equilibrium and so on. The thing is, to compute this equilibrium in an efficient way, you can also use off-the-shelf tools, simply because the cost functions involved are new, of a new kind. Like the theory behind these things has not been developed. Now, about going back to the original game, I think that the interesting thing is that one might decide to relax and to go back to scalar, but I think there is a fundamental difference in doing this after you solve the game, right? If you prescribe, in the beginning, you're like prescribing everything about your model, whereas at the end, it's a conscious choice, right? You might say, okay, now I have all this equilibria, there is a trade-off between these quantities. Now you sit down with the regulators and you say, okay, we choose to place ourselves in this point, and so we relax this way. Whereas in the beginning, you could not do that. This was simply not possible because of the structure of the game. Thank you. And I'm happy to discuss offline if there are deeper questions.
Let's give Gioele a big hand. Thank you for that. So, very enlightening talk at a multi-scale talk. So I'll just give a quick announcement as to where we are at and what is following next. So we have our final session with the contributed papers, and that will cover. Let me just get to that. That will cover our 7 different papers. So it'll be really worth the time, because in 1 hour we will actually get 7 very interesting ideas over here. And also just a final announcement. So this starts at 4 o'clock. So if we can reassemble a minute or 2 before 4, that'll be great. And also from tomorrow we will to Wednesday, we will actually be hosting, like, the real iteration of Mad Games in person with the F110 autonomous racing. That'll be in the main competition and poster area. And you'll get to see 1/10 scale autonomous racing cars competing against each other. There'll be time trials on Tuesday and then head-to-head races on Wednesday. All right, so we can break for the coffee and be back right before 4. Yeah, and if any of the contributor speakers have posters, you can keep them outside.